Okay, so good morning everybody. So let me, before starting this next lecture, I think it will be nice to just a brief recap of what I did last time, so that you know we are on the same boat. So what I was, basically the main physical system that we are interested in is just a bunch of particles in any dimension, but okay, I was focusing on one dimension. But typically these particles are subject to an optical trap. And then I first discussed about the equilibrium properties of this. That means if it is in thermal equilibrium with a heat bath at some inverse temperature T, then we know that the stationary state is given by the Gibbs-Boltzmann distribution, and you just need the energy function basically. And then we focused on energy function has external potential term as well as the interaction term between different particles, pairwise particles. And we said that basically that if there is a long range interaction, that's usually very strong interaction. And we also actually and in general that makes the problem very hard, even though you know the stationary joint distribution of the particle positions. In practice, to calculate any object in the presence of interaction is very hard. We saw some examples from Sylvia's lecture also, log gas, Riesz gas, etc., etc. Okay. But then there is one case which is the ideal gas when there is no interaction. So in that case, the joint distribution in the stationary state, equilibrium state, factorizes into individual distributions. And for that case, for IID variables, we could compute all the observables exactly in principle. Okay. So that will be important for what I'm going to talk today actually. And then after doing this equilibrium, then we wanted to drive the system out of equilibrium. And the main problem in out of equilibrium is that now you can do out of equilibrium drive the system in many different ways, but we have these particles and we want to somehow, so there the energy function is no longer an important observable. I mean, because the Gibbs-Boltzmann distribution does not hold, detail balance is typically violated. And therefore, the dynamics decides the fate of the system at long times. And then, the main problem is that we don't even know what the stationary joint distribution is. That's a problem number one. And the problem number two is that even if we know, I mean, we cannot calculate, so it's not easy to compute any observables because if there are strong correlations between particles, okay? So we wanted to actually find some simple models where we could drive the system out of equilibrium and have a very strongly correlated non-equilibrium stationary state, and yet we can calculate all these physical observables exactly. And to achieve this goal, to find such solvable models, what we said is that okay, I mean, one way to drive of course you can drive a system in many different ways out of equilibrium, but one simple way is by the stochastic resetting that I talked about at the end of my lecture. And the stochastic, and then I illustrated this with the example of a very simple example, which is a single particle. So you take a single Brownian particle, and so it just diffuses freely, and then after some typically exponentially distributed random time. So these are the sort of time intervals between successive resettings, and if you are talking about a Poissonian example, then this R parameter R is the rate of resetting, and so with this rate of resetting, so then we sort of we saw that just this simple example, it drives the system out of equilibrium. And in fact, for this example, I mean, we actually could compute very simply the full probability distribution of the single particle at any time t, and the answer was just from the renewal, so this has renewal, which is very important actually. Because the process renews itself after every resetting. So essentially, so what we have is, so this is the first term, which was without resetting, when there is no resetting, and when there are one or more resettings, then we said that it's enough to look at the last time since the last resetting. So t last is the time at which the last resetting happened before t, and then we just look at the time difference And if I know that, then the point was that, I don't care what happened before that, because I know by resetting that, this was the resetting, so it starts at the origin, and therefore after that there is no resetting, so it's a free propagator over a time period tau. So I just need to know what is the distribution of this tau, because this tau is a random variable, and distribution is simply, it's a Poisson process, so there is no resetting, no resetting, no resetting, followed by one resetting, which means R d tau, which is the probability that a resetting occurs exactly between time tau and tau plus d tau, and this is the probability that there is no resetting during this time interval. Okay. So this was a very, very simple structure, and in particular then we saw that as t goes to infinity, this first term drops out, and so this is the stationary state. Just use this notation, which is simply just this integral r 0 to infinity d tau and you can do this integral explicitly, and its answer is half square root of r over d exponential minus square root of r over d times small x. Okay. So this is the length scale here, square root of d over e and d over r, which is just the typical distance that the particle travels between two successive resettings. Okay. So it's a very simple stationary state, which is double exponential like this, with a cusp at the origin. And the cusp at the origin, it happens because you are all the time resetting to the origin, so there is a higher probability there to be to dynamically resetting to this point, and then it decays exponentially on both sides. Okay? And as I said, this has been also experimentally measured. So today I want to do, to connect up with the first half of the talk, which is to multiple particles. I want to do, the multiple particles and out of equilibrium, and this is, and the important thing was that this was a non-equilibrium stationary state, because the resetting violates Dittel balance. So I want to do the generalization now to multi-particle systems. And I want to, just create a gas which is out of equilibrium, which is driven by the stochastic resetting. So it's a multi-particle point processes out of equilibrium. Now, before I do that, I want to just tell you a little bit about the actual experiment, because this whole work was motivated by experiments. Let me just tell you a little bit about how actually one does this experiment. Okay, so basically, a few years back, I was in giving this talk on stochastic resetting in a conference in Stockholm, and there was Sergio Siliberto, who is an experimentalist from ENS Lyon. And he works with these colloids in optical traps and so on. So he asked me that, okay, so this is nice theoretical model, but how do we actually do an experiment with this in let's say an optical trap setup? Okay, because theoretically it's very easy, because you just say that, okay, your motion is just either Brownian with probability 1 minus r dt, and with probability r dt you go back to the origin. So it's very easy to implement the resetting. If you're doing numerics also, that's also very easy to do. You just evolve it up to a random time, and then just instantaneously you reset to the origin. Okay. So, but in experiments, how do you do that? If you have some colloidal particles in an optical trap, how do you actually set up your experimental procedure? Okay. So he came up with this following protocol. Maybe I'll just take my notes. So The main difficulty was this, how do you actually mimic this instantaneous resetting? Okay. Free diffusion is easy because you switch off the optical trap. Okay. So imagine the following thing. So you have, just a line here, and you have an optical trap which you can switch off or switch on the way you like. And let's say you have just a single particle. Okay. So his protocol is the following, and let me draw a picture here. So he said, okay, this is space, time. So you start from the origin of the optical trap. So you switch off the trap first. You let the single particle diffuse exactly up to a random exponential time, which is drawn from, let's say, r e to the power minus r tau 1. And after this time, then you switch on an optical trap. Okay. And I'll tell you what is this interval. So here is a free particle, no trap, and here you switch on the trap, harmonic trap. Okay. So if you like, the equation of motion here is the type 1 is just noise. So this is just a noise, white noise. Whereas in phase 2, this is 1, 2. Phase 2, the equation of motion changes, just becomes minus mu. It becomes a Ornstein-Uhlenbeck process. Okay. What is the point of this? Because you want to mimic this instantaneous resetting to the origin. But of course, that, how do I do that? So he said, okay, so let's switch on this optical trap, and then this particle will move inside this optical trap, which will try to confine the particle. So its motion, instead of growing like square root of t, it will be of order 1. So it will just become very sort of around the origin. It will just fluctuate like that. And we know that if you take an Ornstein-Uhlenbeck process and you wait for a long time, then it reaches a stationary state. And the stationary state is simply Gaussian. So this is up to some normalization constant is just mu x square over 2d. So mu is the stiffness. So this is mu by 2x squared. So mu is the stiffness of this trap. Okay. So that means basically, and during this time you don't make any measurements. Okay. So you evolve with this. You just let the particle relax to its thermal equilibrium. And if it relaxes to thermal equilibrium, then you know that the particle position now is distributed by this. So this is like, instead of resetting instantaneously to one particular position at the origin, you are actually resetting to a distribution, which is a Gaussian distribution, thermal distribution, depending on this trap thick, and you can control the stiffness of the trap by control this width of this distribution by changing this mu, basically. Okay. And so the idea was that, okay, so you switch on this trap, you don't make any measurement, you just let the particle diffuse freely. Okay. And then if you make this mu to be very high, so suppose that mu is almost very, very large. Okay. So then you see that, when mu is very large, this guy essentially, goes to a delta function. Okay. So therefore, you can, by this, you can mimic this instantaneous resetting to the origin if you choose your stiffness to be very, very high of this trap. And so you let, and they have a technique. So you can say, but then I have to wait for infinite time to reach this. How can I do the experiment? So these people, they have developed something. Okay, I don't know very well these techniques, but it's called the engineered Swift equilibration. So by this technique, if they know the stationary state, they can actually go there very fast. Okay, you don't have to really wait for infinite time for the system to relax. So you can actually do it in a measurable time scale in the lab, basically. Okay. So you let it system. So that's like, so this phase here exactly sort of mimics this resetting here. And then after that you switch off the trap. So you go back to phase 1 again, and the particle freely diffuses in space. So again, it's sort of normal Brownian diffusion. And again, after some random time drawn from the same distribution independently of tau 1, you switch off the trap, you switch on the trap, and you go to phase 2. So then you sort of becomes like this again, and so on. And you repeat basically, alternate. So these two phases alternate, and then that is sort of exactly, if particularly if you choose this mu goes to infinity, mu to be very large, then it exactly mimics this model. Although okay, so this is a way to do these experiments, but the point about the experiment was not just to mimic the theory, because then what is the point? You can do the calculation yourself and numerical simulation. What is the point of doing experiments? But these experiments actually led to many new questions, which is what I want to tell you about. So first thing was that the effect of the finite sigma. So that actually led to a lot of interesting properties on first passage property. But since today I'm not talking about first passage properties, I'll just fix on the stationary distribution. So one of the things that happened during this experiment is that he said, well, this particle, it's almost impossible to find one single particle, because these particles are in a liquid. There's a liquid and there are interactions between them. Okay, so how do you actually, doing an experiment with single particle is not that easy. Okay, so that raises this question that imagine that now we have many particles here. Okay. And you are doing this exactly the same protocol basically. Okay. So I have a bunch of particles, then I let them diffuse freely up to some random time, and then I switch on the optical trap, and then I again let them diffuse, I switch on the optical trap, and so on. Okay. So essentially this is a many particle stochastic resetting, if you like. And the important point is that when the resetting happens, because they are all in the same trap, so they get simultaneously reset, right? So and this is important because they are in the same trap, so the trap moves and therefore all the particles feel the resetting at the same time basically. Okay. So now in general, of course, these particles are interacting, meaning that they are in a fluid, which means there is hydrodynamic interaction between them. And to solve this problem of interacting many body particles subjected to simultaneous stochastic resetting is not that easy. Okay, so because of this interaction between the particles, so therefore we wanted to first, as a sort of reference problem, reference model, if you like, we wanted to so if you like, in statisticians would call it null model. So imagine that there is no interaction. Okay, so switch off the interaction. I'll show you some data later, okay, between particles. Okay. So then you have a very simple model, right? So you just have a bunch of independent Brownian particles, okay? and they are subject to simultaneous stochastic reset. And I will assume that the stiffness of the trap mu is very large, so that it's a, instantaneous simultaneous resetting to the origin. Okay, so the typical trajectory of the system, if you like, is that again this is space, this is time. So all the particles, they start from the origin, and okay, I don't know if you have different color. It doesn't make much difference. Okay. Etc. So this is n equal to 3, and then after some random time tau 1 drawn from you can choose any distribution you like, but this is the simplest thing, so I'll just stick to this Poissonian resetting. And after this, they all simultaneously get reset to the origin. Okay, they can cross in between because they are totally independent. Okay, and then again they start from the origin and then they move. And again they reset after some random time simultaneously, this tau 2, which is also drawn from the same distribution, and so on. Okay, so that's the system, and I want to know that so if I look at that fixed time t, and so I'll have a point process there. So the positions of the particles, so they'll form a point process. Okay. And I want to know what is the joint distribution of the positions of the particles. So I put a subscript r here to denote that this is resetting. Okay. So I want to calculate the joint distribution of the positions of n particles at time t. So that's the problem. Okay. So once again you realize that this is actually, once you know the single particle thing, this is again quite straightforward. So let me denote the time of the last resetting by t last, and I'll call the time since the last resetting as tau. And again you can invoke this renewal picture, and you don't care really what happened before that, because you know that since the last resetting, they have free propagation. Okay, so one guy goes there, another guy goes there, another guy goes there, etc. So this is my last resetting. Okay, so exactly in analogy with this single particle thing, I can then write down this object as so this is the term when there is no resetting, because you could have some realization when there is no resetting event in between 0 to t and just a free propagator. So free probability that there is no resetting is e to the power minus RT. And then when there is one or more multi-resettings, so we can just look at just this last interval exactly in the same way as we did before. And because it's a free propagation during time tau, so that's it, and this is the exact measure probability distribution, joint distribution at any time t. Okay, and it's very simple interpretation in terms of these renewal times. Okay, so we have this, but first let's see. So first thing you notice that at any time t, including in t goes to infinity, that this is not factorizable. I cannot write in the product form basically. So let me write it this way. Because there's an integral over here. So inside the integral they are product form, but in general they are not product form, which means that there is correlation between these particles at any finite time t. Okay. Except at t equal to 0, of course, they are. Okay, so let's first try to calculate, to guess this correlation function, calculate this correlation function.
Yes. So, Satya, so you could get this answer from thinking about the field that receives this, and then after, at some rate r, it goes to a Dirac delta. It's like you can get the same answer.
I don't know why you want to do the field. I mean, this is simpler, no?
It's just another way of...
Maybe you can do it, but I can guarantee you it will be much more complicated. This is the simplest way to get to this, guess to the answer. Okay. So correlation. So what is the correlation? So normally the correlation function you will measure just by this object, connected correlation function. This is the connected part of the correlation function for I not equal to j. I'll discuss the physical origin of this correlation in a minute. Now this guy, you see from this structure here, okay? So this is our key equation. So if I calculate xi xj for I not equal to j, you see this is a Gaussian, so therefore xi average, this will give you 0, x and xj average, because they factorize within this. So this is clearly 0 from this term, and it's also 0 from this term. So this object is identically 0 at all time t, just by the symmetry of the problem. So therefore, to detect the correlation, you have to go to higher order. Okay?
So one question. If you think of this as n-dimensional order motion,
I'll make the remark exactly. No, you can think of exactly, absolutely right. This is, you can also think of this as the single particle in n dimension, and this is just the different components of this. Okay, but the thing is that ultimately I want to think of it as a gas of particles. Okay, and so for observables like order statistics or full counting statistics, if you think of them as components, it doesn't make much sense, right? I mean, why do I order the different things? But if you think of them as the positions of n independent particles as a gas, okay, as in the sort of real system, so then it's better to interpret that in as independent particles basically.
Did you get the closed form as you have in
Yes.
Okay.
Yeah, you can write in terms of Bessel function. But I don't want to do that because this form is, this integral representation is much better to calculate the observables. All right, so we have to go to the next, higher order correlation function, and so natural next order correlation function is just you look at xi square, because again this is the x goes to minus x symmetry, so therefore this object is always 0. But I now want to look at, to get something non-zero, you can calculate other types of correlation functions also, but this is the easiest thing to calculate. And this is very easy to calculate, right? Because, if you just multiply it by xi square, xj square, you see that, because they factorize, so you can calculate for ith particle and for jth particle. So that will be just 2 dt times 2 dt from this term. And similarly here, 2 d tau from this term. And you subtract off, and you can trivially calculate this. So I won't do the calculation, but so let me call it this Cij t, I not equal to j. So the answer is, I can write in a scaling form where this fc is a scaling function, and what is fc? Okay, so this function, if you plot, this subscript C is for correlation basically. So this is a natural time scale. I mean, 1 over r is the rate. 1 over r is the time scale between two resettings. So this is a natural. So it actually, this function, if you plot, so it approaches to 1 as z goes to infinity. So the asymptotic behaviors are it goes to exponentially fast as z goes to infinity. But for small time, small z, it actually grows like z cube over 3. Okay? So that means it goes like t cube, time cube. So you see that the correlations, they actually form and they are growing with time. And then finally they saturate at long times to some constant value, which is 4d square over r square. Okay? So the correlations, so that's why I call these correlations as a dynamically emergent, because they are not built in. You know, these particles are basically non-interacting. There is no direct interaction between the particles, but they get correlated because of this simultaneous resetting. You know, this is the key point. So it's like, you know, I mean, if you think of, you know, why in the beginning it was a bit strange to find these correlations, but you know, with a little bit of thought you can sort of rationalize it. I mean, it's like, you know, imagine that you are in this room and each of us is carrying the same bell, okay, and so we don't know each other, we just go around, roam around, whatever, but whenever the bell rings, so we all have to come back to this room, okay. So dynamically, at random times, you are coming back to this room, and that actually creates correlations between you. Okay, so this is a sort of you know, physical reason for it. So that this is a, and you see that this correlation is strong in the sense and long range because it's true for every pair of particles. So this is exactly the same correlation for every pair. So just like in the equilibrium systems, you have seen, for example, log gas, every pair is, you know, has a log repulsion between them. And here, of course, there is no interaction. I mean, it comes dynamically from the, because it's an out of equilibrium system. So for every pair, Ij, so they are correlated. And this is an attractive, effective attractive interaction, as we'll see in a minute, a little bit later. Unlike the log gas, which is a, you know, which is a repulsive interaction between the particles. And attraction comes from the fact that because of this simultaneous resetting, you know, trap switches off and on, so they come closer together. So effectively, it creates some kind of attraction, all-to-all attraction. So that's a key word. Between these particles. So they get, and you see that in the long time limit, okay, so now I do the stationary state. I mean, you can analyze this problem at any time t, but I will focus on long time stationary state. So we have this, our key formula over there. So I take the large time limit. So the first term again drops out. And the second term is just you have an integral, which is, so we are stationary now. So it's very simple, you know, it's explicit non-equilibrium. First of all, it's an out of equilibrium. So this is again, because stochastic resetting, you know, violates digital balance. So this is an S, non-equilibrium stationary state, and you have the joint distribution explicitly, and that's the first point. Second point is that in the NES, they are strongly correlated. Strongly in the sense long range, that means everybody is correlated with everybody. And you see this correlation function, I mean, it goes to long time limit, it goes to this constant 4d square over r square. Okay.
But why is it interesting to say that everybody's correlated with everybody since they all draw?
Sorry, say it again.
Why is it interesting to say that everybody's correlated with everybody in the same way? Because they're all very
No, because this is a strongly correlated system. As I said, you know, to calculate any observable, okay, in all these long range systems is very hard because of the strong correlations. So if you have a weak correlation between, but let's say I'm correlated only with my neighbor, okay, then there are techniques usually, I mean, like, you know, renormalization group or perturbation theory you can do. But if you have a strongly correlated system, you know, it's very hard to calculate any physical observable. Okay? As you saw, for example, from Sylvia's lecture, I mean, the you know, log gas or these things, you know, log gas is particularly difficult, but okay, I mean, thanks to the determinantal point process nature there, we could calculate many observables exactly. But in general, they are very hard. Okay. So, so both equilibrium and out of equilibrium, I mean, even if you know the stationary state explicitly, when there are strong correlations between particles, calculating observables is extremely hard. That's the main point. Okay. And so this particular structure, what you see is, you know, it's not factorizable clearly because of this integral here, but it's factorizable conditioned on tau. So tau is a random variable, okay. So tau is a random variable here. So conditioned on tau, so in other words, you know, this basically has this structure, I mean, general, you know, structure like something like this. So let's say some random variable u, some distribution of this random variable u, and you have this, you know, p0 of xi given u. So it's like, you know, suppose that this you know, whatever your individual distributions, they are, you know, they are conditioned on u or parameterized by u, and then this parameter u, it has a, you know, PDF, this is the PDF of u. And this parameter is a random variable which is drawn from this h of u, and then you have to integrate over all possible values of h of u. Okay. So that's the structure. So this is what we call, you know, CIID structure, or conditionally independent So it's not IID, but slightly more complicated. And so this is a general definition of a CIID structure, and in this particular example, so you see that immediately that you identify this random variable u with the tau, where tau is just the time since the last resetting. I mean, here the structure of the problem was that we could easily identify this, okay. It came out naturally. And h of u, that means, you know, just p of tau, which is okay, so this is the Poissonian distribution. And later on we'll see that there are many other problems where you have exactly the same structure that comes out in the stationary state, is in the stationary non-equilibrium state. And but sometimes, you know, it's not easy to identify. It has a hidden structure, because if I give you the joint distribution, it's not always clear that you can write it in this CIID form. Okay? And you will see that, you know, this is not always easy to identify this random variable, you know, the relevant random variable which comes into this particular solvable structure. Here it's, you know, explicit, because here is the time since the last resetting by construction, basically. Okay? And but the advantage of this particular CIID structure, and you know, this is, I come back to Thierry's comment that, so remark. So this object so you can, you know, you can think of this is also the position distribution in the stationary state. Of a single particle in n dimension. So in one dimension, you know, the integral is very simple. It's just this. In any n dimension, you can actually do this integral, and this integral is just, you know, some Bessel function, modified Bessel function with some index here, n minus 1 into something like that. Okay, there's some r somewhere. I mean, the square root of p over r. Maybe there are some factors which I don't remember. But anyway, you can do the. But I mean, I don't want to do this because I want to keep this integral representation here, because the main point is, and this is the sort of crucial point, because I remember I said I am looking for models with three categories. So one thing is non-equilibrium stationary state is driven out of equilibrium. Second thing is that it should be strongly correlated, because you want to find some solvable model with strong correlations. And the third point is that it should be solvable for all observables. And the observables I defined are like overall, you know, both macroscopic and microscopic. So picture is that you have a gas of particles which is driven out of equilibrium, point process. Okay, so you have this, yeah, this guy here. Yeah, you know, the positions of the point process. It's in a stationary state, and you want to calculate both macroscopic and microscopic observables. Macroscopic means I define the, for example, average density of states. That's the first object, which means average density profile, which is so this just counts basically the fraction of particles between x and x plus dx. Okay? And so that's the macroscopic one, and then several microscopic one I defined, like order statistics, gap statistics, full counting statistics. Etc. So we want to calculate those things, and what I want to show you in the next few minutes is that all of them you can actually calculate it exactly explicitly because of this CIID structure. Because you see that, if I want to calculate any observable, so all I have to do is again the same thing, again exploit the renewal structure. All I need to, so I first I condition on tau, I fix tau, and then I know that they are all IID variables, ideal gas. And I have shown you how to calculate the observables for ideal gas explicitly. So all you have to do is to calculate this for IID distribution drawn from the Gaussian with tau as a parameter. You have explicit formula for those, as you have seen, so the ideal gas, and then you just have to average over this parameter tau drawn from this Poissonian distribution. Okay? Because that's exactly the picture, right? I mean, I have a gas, I go with my microscope, I look at the average density profile here, I look at the gap, order, etc., blah, 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 all these things. I just compute them for fixed tau, and then I just, have to average over tau. Okay? And calculating for fixed tau is easy, and I've shown you explicitly, and that's the reason why I did the ideal gas for equilibrium. Okay? Problems. I mean, because this is just just IID variables basically. Okay, and so that's the way to do it. Okay.
So we can just show you. Yeah.
So I guess there are two extremes from the time to its last resetting. One this is really small, and one this is really large. So I guess
what is small and large?
So there's two regimes. If I reset a lot, and then when I reset
as a function of R, you are thinking.
Yes, as a function of R. Yeah. So when I don't reset that often, I should regain this factorization structure.
Yes.
And this can be shown.
Yeah. Because you have to be careful. You have to do it at finite time t, because you have to, here when I look at the stationary state, I've already taken the t going to infinity limit. Everything is contained in these things. I mean, if R is if time is much less than 1 over R, then you will see the normal diffusion, factorizable to whatever. But if R, if t is much bigger than 1 over R, that's the time scale. Because when you reset that's the one which drives you out of equilibrium stationary state basically. You have to reset many times, and then you have a different regime, of course. Okay? But if I'm just focusing on the stationary state, I cannot take R equal to 0. It doesn't make sense because I've already taken the t going to infinity limit there. Okay. Yeah, I should say that maybe I'll just give you a few references. So this model of simultaneous resetting particles and this main result, which has gone up somewhere. Yeah, that one over there. So this was actually the work of actually all these references are there in the main things, but I'll just write down. So this was okay, so sometime in 2023, I don't have the, it's there in the website, the main reference. And the original experiment of Siliberto that motivated us looking at this problem, so those two references I can put it here. So this was before this work, and also this was in 1 dimension, and also we did for 2 dimensions, because all these problems you can actually define in any dimension, just a Gaussian propagator instead of xi square. Xi is just a vector now. Okay, so I was commenting on the just didn't finish it. Right, so this you can think of a single particle in n dimension, but the thing is that we don't want to think that way, for the reason simple reason. First of all, for the physical reason, these observables, doesn't make sense much if you think of x1, x2, x3, xn as the components of a single particle in n dimension, because this order, meaning that which is the highest component, first component, second component, etc., or the gap between them, it doesn't make much sense, because if you have, for example, two particles, you have a two-dimensional particle. The two-dimensional particle, why would I be interested in the gap between x and y component, or even the FCS and all these things? So they make much more sense when you project them in one dimension. Okay, and that's one of the reasons. And the second reason is that I don't want to also write it in terms of the Bessel function, which you can do explicitly, because you will see in a minute that this, as I said, because this integral representation is very important to bring out this CIID structure, and then you can use it to calculate and use the results of IID variables to compute the observables with this thing and then average over that. I mean, to do that for this representation here, for the exact formula, is much more harder actually. So that's why I didn't want to think of it as a one single particle in n dimension. So now I just list some of the just to show you some of the properties of this gas, some explicit computation of that. Where is the eraser? Yeah. Okay, so again the picture, always keep this picture in mind. So you have a gas or particles in one dimension, and we know that in the stationary state the joint distribution is so there is, first of all, there will be some average, so this is inside this is joint distribution, so there will be some average profile, and we want to calculate this average profile. An average profile is average density profile, so A. So this is, as I said, by definition, it just calculates the average fraction of particles between x and x plus dx, normalized to 1. So this is, by definition, here if you integrate this guy, this is 1. So it's a fraction of particles between x and x plus dx, the density basically. And so, I mean, and this average is here with respect to this joint distribution. Okay? So if you just put it there, then immediately see, because this is exchangeable, x1, x2, I mean, if you exchange x and x3, it's the same. So therefore, this is just the marginal distribution of one single variable. And marginal variable is precisely single variable. I mean, you just have to integrate over, if you integrate over from, let's say, 2 to n, keeping the first one as x, so they give you 1, and so it's just the stationary distribution of a single particle, right? So it's exactly that, half. Okay. So this is precisely the average density profile. So first thing to notice is that this is independent of n. Okay, so in this simple gas, and here I want to just as a comparison basically. I mean, just to connect up with the first lecture in the equilibrium log gas. So 1D log gas. So 1D log gas means that you have an energy function which is this external potential energy, and then you have this log repulsion between the particles. This is what Sylvia has shown you. So let's say, and we just for simplicity we keep beta equal to 2, which means the joint distribution of this log gas up to some normalization. So this is the GUE, Gaussian unitary ensemble. So this is the eigenvalue distribution, joint distribution of the eigenvalues of a Gaussian unitary ensemble. So for this case, if you calculate the rho xn, and again I'm using the same normalization as rescaling as Sylvia did, because by multiplying this by a factor n, so that both terms are of the same order. This is a pairwise interaction, so this is a term of order n into n minus 1 or order n square for large n. This is also order n square for large n if xi is of order 1, and therefore, and if you compute this, so then essentially what happens in the large n limit, this goes into a semicircular form. So that means all the particles here, so here it's root 2 and minus root 2, and so you have this gas of particles which are in a finite, in the large n limit there is a finite support. So basically the reason is because, you know, if you think of these two energy terms, I mean this guy is trying to push all the particles towards the origin, okay, trap center, whereas the repulsion is trying to spread them apart, and as a result, you know, they settle down in the large n limit into an average density profile which is between minus root 2 to plus root 2, and this is so rho xn in the n going to infinity limit converges into this is called the Wigner semicircular form. Okay. But this is only in the large n limit where this goes into this form, and here you see that, you know, this is completely independent of n. And first of all, other difference is that here we have an infinite support. The gas is actually spread all over the space from minus infinity to plus infinity, as opposed to the log gas where it's actually confined over a finite region of space. Okay. So then you can actually, so this is very simple to calculate the average density, and so next I want to calculate the order statistics. So which means basically I order these particle positions so that M1, M2, etc., they are the same particle positions, but M1 is bigger than M2. So I just consider this gas. So this is the rightmost particle. Its location is M1. Second rightmost is M2, etc. Okay. And I want to know what is the sort of distribution of the kth rightmost particle, right? So probability in the stationary state. So once again, the stationary state, I mean, as you saw here, oops, where is it? It's gone somewhere. Okay, so we know the stationary state explicitly, and yeah, it's here actually. So you see that all I have to do, once again from the same picture, that I have to just compute but this is just the order statistics of the ideal gas. Meaning IID variables which are drawn from this, let's call it P0 of x tau, psi tau, where this P0 of x tau is just a Gaussian. Okay. So, and by the same, exactly same renewal argument, that means, I mean, if I'm looking at a very long time t, all I have to look for is what happened before, since the last resetting. So, since the last resetting, currently I have a stationary gas which is IID distributed with this parameter tau, and I had given you this formula here for IID variables. So it's tau is a parameter here. So this is just n factorial by k minus 1 factorial n minus k factorial times P0 of W tau times and this was just a very simple thing, it's just IID variables. So you have, if you fix the kth guy to be W, then you have to have k minus 1 guys bigger than it and n minus k guys smaller than this, and then there's a combinatorial factor here, and so this is the exact formula. So all you have to do is to just substitute this exact formula here. But this P0 x tau is just a Gaussian. So you have an explicit formula for any n actually, and for the order statistics for this gas. And then okay, to carry out this thing is a little bit difficult, even if they are Gaussian, these things. But you can easily take the large n limit. So in the large n limit, what happens? I mean, I won't do it in great detail, all this, but just sorry. Yeah. So large n limit, you just have to use the Starling's formula for factorials. So this is n to the power n plus half, okay, square root of 2 pi e to the power n minus n, or something like that. And you have to, so now k, now here, I mean, again, in the log gas, it's known that the behavior near the edge and near the bulk, okay, near the trap center, they are very different. So typically, of course, the separation between these guys is of order 1 over n. Whereas, so k, you can set k now. K is the, so I can set k equal to alpha n. Okay, so where alpha is a number between 0 and 1. So when alpha is order 1 over n, then k is of order 1. That means I am probing near the edge. Okay. But if alpha is of order 1, then k is of order n. That means I am probing deep inside the bulk. Okay. So this is the bulk, and this is the edge. So you can set k equal to alpha n here, and take n large limit, and you just work it out. And I won't go into the details, but basically what you find is that so first do it for fixed tau, and then in the large n limit it goes into so first for fixed tau, you just just look at this part here. That means this part. You do it for large n, and what you see is that in large n limit, so W star is such that and this is just for IID variables, I mean, essentially. So this is okay. So you have this, bunch of particles, and so you first fix, they find out the W star such that the fraction of particles to its right is alpha. So it's like a quantile, basically, alpha quantile of this. So and P0 is just a Gaussian. So from that you can figure out what is W star as a function of alpha, and then the kth maximum, the distribution PDF of that. It's actually a Gaussian distribution, just centered around W star, okay, with a width which is of order 1 over square root of n, okay, and then there's some prefactor here. Okay. So this is the sort of large n behavior for any fixed tau, large n behavior of this kth maximum for Gaussian distributed IID variables. So you have to just plug in there and then work out this integral over tau. I won't do it detail, I'll just tell you the final formula. So in other words, what I'm saying is that mk tau as a random variable, if you like, it goes to a constant W star of tau plus a fluctuating plot P0 W star is evaluated at the W star quantile times a Gaussian random variable n01, 0 mean and unit variance. Okay. So that's a statement in terms of probabilistic statement, which is exactly equivalent to saying that this is the thing. Okay. So, And so what happens here is that when you actually now do this integral, okay, then it turns out that this term, the fluctuating part, only contributes to lower order. The leading order behavior is just comes from the deterministic part. Okay. So therefore, you know, probability to leading order, if you are interested, you can do it systematically, but you know, do a large n expansion. But leading order, it's enough to replace this whole object by its expectation value, namely okay. This fluctuating part actually gives rise to lower order corrections. Okay. So therefore, you know, essentially, and you can evaluate this W star by just putting this Gaussian thing here. What you find is that W star so our complementary function is defined as it's a little bit of detail, but I mean, I'm just main point to understand. So and this is the inverse of this. That means, you know, give me, if you give 2 alpha here, then you have to invert. This is just exactly this quantile relation. So you get this W star, which just basically goes like square root of tau into some number. Okay, you put it there, and then you can do this tau integral, and the final result is that so the probability of mk equal to W, therefore in the large n limit, it converges into a scaling form. I'll write it down first. Where you remember that k is alpha n. So I'm taking k large, n large, keeping alpha fixed. That means I'm probing the bulk, if you like. And where this lambda alpha, the scale factor, is just square root of 4d over r into this. But the scaling function f of z is completely universal in the sense z positive. Okay. So what this means, no matter, you know, whether I'm looking at the first guy, second guy, third guy, etc. I mean, if you're probing at the edge here, then of course you have to take alpha to be of order 1 over n and do the expansion, and this function doesn't change. The only thing that changes is that now it will be, so when k is of order 1, which means alpha small. So alpha small, you can just, you know, expand this guy for alpha small, and what you find is that the lambda n is actually square root of log n. Okay. So that means if I look at in my gas here, the typical size, you know, typical location of the rightmost particle, it scales like square root of log n. Okay, scales like square root of log n, and its distribution is actually given by first of all, I mean, it's, you know, it does get, you know, it has no zero support on the negative side. I mean, in principle, this M1 can be negative also. You can push all the gas to the negative side. Okay, so it's nothing is, but in the large n limit, it gets supported only over the positive side. Okay, there is no support on the negative side, and the scaling function is exactly given by a very simple form, which is 2z, and this scaling function is totally universal in the sense it doesn't matter whether you are probing the 10th particle, 15th particle, etc., or first particle, second particle, etc. Only the scale factor changes. This is very different from the log gas, because the log gas, as you know, is that if I look at the maximum, which is the k equal to 1, so maximum actually has a Tracy-Widom distribution. So there is a scale here, which is of order n to the power minus 2/3. So the maximum lambda, x max if you like, or m1, in this case, m1 is square root of 2, which is this as a random variable, is square root of 2 is a deterministic part, and then there is a order n to the power minus 2/3 into some random variable chi, and this chi is this famous Tracy-Widom beta equal to 2. Okay. So this distribution here has non-Gaussian tails. It behaves like exponential minus mod x cube on the left side and to the power 3/2 on the right hand side. So it's a Tracy-Widom distribution. But if you look at the ordered maximum in the bulk, they are quite different. Okay, so bulk and age are very different. Whereas in our problem, bulk and age, all the order statistics are given by the same scaling function, universal scaling function. So this is universal. Only thing that changes is the scale factor, basically. Okay. Sorry.
Look at the n's.
Yeah,
Last
exactly.
value.
Even
Can
if
it be negative?
yes, yes.
That's surprising.
Think about it. Yes. Yeah, exactly. Even if you look at these things. No, sorry. No, you have to be a little bit careful here. This alpha, because when you go probing the other side, there's a symmetry factor actually. So it will be exactly opposite, because alpha becomes negative, right? Alpha is when W star becomes negative. Okay. So there's a symmetry. So if you look, for example, on the other side, meaning that the last guy, okay. Last guy is supported only over the negative side. This is exactly reflection of that.
Okay.
So this is for, I should have said that this is for alpha positive. Alpha negative, you just have to.
I guess what confused me is that this word k is alpha n.
Yeah. Sorry, alpha bigger than half. Sorry, alpha bigger than half. Sorry. Yeah. You're right. Okay. For alpha less than half, it just goes in the other side. It just gets reflected to the other side. Yeah.
Can you compute any observables in the presence of an external potential? Like if I put this gas in a box, can you tell me its stationary density?
Yeah. This, you can try to do that. And actually, it's not that easy. Actually, even in a box. Actually, this problem in a box is much more difficult. Okay. So it's much easier if you do it in a harmonic potential, basically. I'll discuss this a little bit tomorrow, actually. So in a box is much more harder, because the propagator in the box, if you have reflecting boundary conditions, is not a simple Gaussian. It will have the cosine and sines and all these things. So it's to manipulate that thing is a little bit harder. That's all. It's technical reason. Okay, so then I focus on the gap. So gap means the distance between the kth and k plus 1th particle. So the gap. And this is the, in the Wigner case, in the log gas case, this is a object which is much well studied in the, starting from Wigner. And again, it's known that the gap distribution near the edge is very different from near the bulk. Okay. So near the edge, it's of order n to the power minus 2/3, whereas here it's of order 1 over n. Okay. So because these particles are very close to each other near the bulk, because the density is high there, whereas here they are sparser. Okay, so this typical scale here is n to the power minus 2/3 around this root 2. So the picture of the gas is that, okay, you have a dense gas near the trap center, and then as you go away, it becomes sparser and sparser, and the typical gap goes like n to the power minus 2/3 near the edge, and in the bulk it goes like order 1 over n. So we can ask the same question here. What happens here? So I have my gas. So this guy is going like square root of log n, and okay. So I'll not, do the in details, but just to again exactly the same computation, basically exploiting the CIID structure, which is all I have to do is to look at the gap for the IID case, and then integrate over this parameter tau. And IID case, I mean, we know how, again, I'm not going to rewrite this formula, but you have to write down the joint distribution of mk and mk plus 1, and from that you can calculate the distribution of tau, distribution of the gap. So basically what we can show is that the probability for a fixed condition on tau in the large n limit, it actually has a very simple form. Just like there it was going to Gaussian, and here it actually goes to an exponential form. Okay, so W star is again this quantile defined here, and P0 is just a Gaussian. So P0. You get the basic idea. Basic idea is that, for IID variables you can compute everything, and all I have to do is to just do it there, take the large n limit, and then just have to integrate over tau. That's it. Okay. And so this is the gap distribution. And now if I just do this integral over here, just after substituting this, so what you find is that this guy, therefore, in the large n limit has this scaling form. Okay, how do I write it? Again, some scale here, which I'll write in as ln maybe. So this is the scaling form is needed to normalize. So you have these things, and so the ln, the typical gap, if you like, behaves like 4 pi d over n square root of r exponential so it's fairly explicit, but it goes like 1 over n. So this is for fixed alpha. That means when alpha is of order 1, which means deep inside the bulk. So that means the typical, as in the log gas, if I look at the spacing here near the bulk, it's of order 1 over n. But if you take now alpha to be very small, that's alpha to, let's say alpha is k over n. So if I take k equal to 1, for instance, or some number order 1 over n, you can work it out how it behaves when alpha goes to 0. And when alpha goes to 0, it goes like, okay, so this is, I said, okay, something like this, up to some number, it goes like square root of log n. So 1 over square root of log n. So that means, the typical, so this guy, the location of this guy is going like square root of log n, and this gap here is actually order 1 over square root of log n. Okay. So in the bulk it's order 1 over n, and here it's 1 over square root of log n. So again, like in the log gas, this also gets sparse and sparse as you go away from the center of the trap. In the bulk they are densely spaced, but at the far away they actually, the gap between them goes like 1 over square root of log n. Okay. But again, this scaling function h gap z, so this is explicit and quite non-trivial. It is normalized to unity, you can check. So you can probably, do this integral and write in terms of hypergeometric function or whatever, but it's non-trivial function, and it has this behavior. As z goes to 0, it goes to square root of pi plus 2z log z plus order whatever. And for large z, it decays actually as a stretched exponential. Exponential minus z to the power 2/3. Okay. So that means it decays, slower than exponential for large z. So if you plot this function, it sort of looks like that. Now this is very different from the log gas case, because you see this gap here does not vanish. This scaling function, the distribution of the gap does not vanish as z goes to 0. In the case of log gas, if you plot the corresponding gap scaled function, it behaves like this. It's called the Wigner-Sermez, or generally you can calculate for beta equal to 2 explicitly. And there it goes to 0, which reflects the fact that they're repulsive. You see, if you look at because of this van der Waals term here, so to the probability of having two particles very close to each other vanishes actually. Okay, and that gets reflected in the gap distribution also. Gap distribution also vanishes. But in our case, the fact that it goes to a constant doesn't vanish, which means that two particles can be arbitrarily close to each other with quite a high probability. And this is the attractive gas. I said attractive all-to-all correlation. So this is actually reflected in the gap distribution, that it doesn't go to 0, but it actually goes to a constant as z goes to 0. Okay. And similarly, you can calculate the full counting statistic. Maybe here I can just, since I don't have time, I just show you some picture and then I'll stop. Can I start this? Sorry. Right. So this is the main point I was trying to say, that that you have this conditionally IID structure, and then if you you can compute all these observables. I showed you already these things. So this is the gap, kth statistics. So you see, this is the picture you have to keep in mind. Order 1 over n spacing, and here it's order 1 over square root of log n. So it gets sparser and sparser. And this scaling function is completely universal, okay, independent of alpha. And so this is the order statistics, and then okay, this is just to show that numerical simulation, it works very well. And this is the gap distribution, and again this gap distribution is independent of alpha. It's the same distribution everywhere, all over your gas basically. And again you see that it doesn't go to 0, and this is a numerical simulation, and this is a totally universal function. Now full counting statistics, I didn't have time to, but it's exactly same method basically. So you have to compute the, you ask, if I take an interval minus L to plus L, and I just ask how many particles are there, okay. So that's the NL, and the probability distribution of NL has this scaling form where NL over N is kappa. Kappa is the fraction of particles in this box minus L to plus L. And you can compute the scaling function explicitly, and this is the answer is given again. Once you give me this kappa, so you have to compute this u of kappa by inverting this error function, and this is some parameter RL square for 4D, and then this function is fairly explicit. And this is actually quite an amazing function, because if you plot it, what you see is the following. So I'm plotting kappa between 0 and 1. So this is the fraction of particles inside the box minus L to plus L. And this is the PDF of that. What is the PDF of the fraction of particles inside the box? So what you see is that here, for kappa goes to 0, it has an essential singularity like this, quite a complicated form. Whereas and it is a non-monotonic behavior. It increases, then goes down, and then finally diverges in a just barely integrable way as kappa goes to 1. Okay? So which means that, and this is because of the again resetting, because kappa, when kappa goes to 1 means that all the particles are inside this box. Since the box I am taking to be minus L to plus L, so there is, with a high probability, there will be always inside this box, and therefore that's why it diverges here, and but diverges in a strange way. I mean, it's kind of non-monotonic. So this is a kind of function that I've never seen before in any of the full counting statistics. It's very different from, for example, from the log gas case. I mean, this is completely different, and yeah. So this is the sort of main point I wanted to talk to today. So what I'll do in next class, tomorrow's lecture, is that I want to show you that this particular structure of the CIID structure. This is actually very general, and it occurs in many other problems, not just this problem of particle stochastically reset, but in other problems, and it's quite a general. So you can have a whole class of solvable models. The main difficulty often, of course, is to identify the random variable which appears here, on which you condition. Okay, so we'll see that explicitly in one example that I'll work it out tomorrow. And so therefore, this was, so I mean, to summarize, I mean, basically these are the 3 things that we wanted to do. We wanted to find a solvable, I mean, we wanted to find a model which has a many body system, which is in a non-equilibrium stationary state, number 1. Number 2, that we wanted it to be very strongly correlated, okay. And number 3 is that it should have some solvable structure so that you can calculate all the observables. And somehow this simple model, it actually satisfies all the three properties, and so that's why we are quite happy that finally we could calculate something explicitly for a strongly correlated system in a out of equilibrium problem. And but as I said, this is much more general, and I want to show you that in the tomorrow's lecture. Okay, so thank you.
Thank you. So I'm gonna take one quick question, and then please.
So you've shown that the effective interactions generated by resetting are attractive.
Yes.
Do you know of any models where this can lead to like a phase separation or a condensation or something?
Good question. I don't know actually. I mean, at least so far I have not found anything, but it might actually. It might lead to some kind of condensation that where they they just to clump up together, for instance. I mean, for example, the active particles or something. If you do you can do the same calculation for same problem with active particles, for instance. I mean, suppose you switch on and switch off the active particles. In fact, Matthis here, he has done some computation when you have these active particles when you switch off and on the tram things. I mean, so you can actually reach a stationary state and condensation transition. And so, yeah.